warmly welcome all the panelists. Of course, I must start with by saying I must also thank the Department of Science and Technology, and especially Dr. Ranjit Krishnapai for from the department for supporting this particular project under the Advanced Hydrogen and Fuel Cell Program. Just a few thoughts from my end. As we have experienced over the last year, we've seen that the greatest amount of warming that we have seen in on the earth on 2023, and we are seeing extreme events also happening throughout the globe. It's an important thing that we are starting to look at solutions from a perspective of climate. India is committed to not only the NDCs at Paris, and then we are going to update them this coming year, but also this commitment that we will be net zero by 2070. And while many of us might believe 2070 is very far away, there is also this challenge of how are we going to decarbonize some of these sectors. And the hardest sectors that we know of are steel and cement, because not only do you have fuel related emissions, but you have also process related emissions. And as we all know, steel and cement are very close to infrastructure development. It is something that we cannot escape. It's something that we have to keep thinking about, especially if we want a developed country with the kinds of infrastructure that we look at for as a developed country. So this brings us to some of the solutions to decarbonize some of these sectors. And I think to some extent, I do like the idea that the government has also proposing through Mission Life, which is lifestyle for environment. And we start thinking about ways in which not only we reduce the amount of carbon that we use in developing cement, iron and steel, but also reduce the amount of cement and iron steel that we'll be needing in our world life. The team will talk about steel making, which is sort of the more important part, and it's one of the hard-to-abate sectors. What I'm really hoping for is, given that it's a very small gathering with some people online, really looking forward to a very fruitful discussion amongst the folks. As I said, this is just the beginning. It is not, usually these events in many cases are the culmination of things. For us, it is actually the beginning of this conversation that we have with regards to hydrogen. It's a long way to go for all of us, but I think the only solution is to go together. So with that, welcome you all and look forward to a fruitful discussion today. Thank you.
Thank you, Jay. I now invite Mr. Murli R, research scientist at CSTEP, to introduce the setting and the context for today's discussion.
Thanks, Merlin. See, the objective here is, before we get to the objective, perhaps I'll just give a quick overview of what CSTEP is and the kind of areas that we are interested as an organization. We are a think tank based in Bangalore with operations in Delhi as well. And our intent is to enrich policy making using science and technology fundamentally. And as far as the challenges goes, so we pursue 4 challenges. First and foremost, it's the clean energy transition. Second is clean air for all. Third is sustainable and secure future for all. And finally, the underpinning challenge is the digital transformation. Now, within all this, we have about 5 key sectors that oversee some of these challenges. So we have, most of them are clubbed in terms of energy, air quality, climate and sustainability. And then we also have other future related topics that are being covered in strategic initiatives. And finally, the digital and AI as a sector onto itself. The hydrogen group per se is fairly new. So we have worked along the entire ecosystem of green hydrogen, be it the production capabilities, technology readiness levels, and things of that nature. While we are also looking at ground up, which is who are going to be the key consumers, their capabilities around absorbing hydrogen in a more efficient way. And finally, we have also looked at the challenges in terms of, is the infrastructure available today good enough to absorb green hydrogen, or should we need upgrades around that? Now, towards these various topics, we have published, and all these information is available in our public domain. So you may be able to read them at your leisure. Now, this project was funded by Department of Science and Technology, as Jay alluded to. And as far as the team goes, now before even we get to the team, my sincere thanks to Dr. Sanjay Chandra. He is currently working in IIT Bombay, professor of practice. But prior to that, he was heading the chief of R&D research in Tata Steel. He has been very instrumental in both devising the project in a much more nuanced way and bringing people together in terms of industry folks to get some sort of a buy-in when it comes to some of these results and finalizing those results. So thanks, Dr. Sanjay Chandra. Of course, he must be able to. He was supposed to come in today. I think there is an event in IIT Bombay as well, so that's all right. Secondly, before I get into the team, it's important to thank the Tata Steel Jamshedpur R&D team for allowing us to visit their plant and having meaningful conversations around to what extent hydrogen can be used. Now, that conversation right at the initial stage allowed us to uh, shrink the scope, so to speak, because it was very wide and we were all over the place, and it helped us in identifying, nuancing the research, and in terms of providing us key insights as to the possibilities of green hydrogen with respect to timeline. While it is theoretically possible, I was talking to Dr. Deependra Kashu as well, Mr. Deependra Kashu as well. While theoretical conversations are important, the practical implementation takes it to the next level in terms of realizing the fruit bearing. So that again, Tata Steel helped us, especially Dr. Samik Nag, who is the chief iron making research group. Then his subordinates, Mr. Sujan Hazra, Mr. Girish S, and Mr. Supratim Sengupta. They all helped us in formulating these ideas and structuring it. So you will be able to see some of that in the report. So if you would want to access the report right away, the QR code right behind the two-pager should be able to enable that. So please scan that and give it a read. Now, additional thanks to Dr. Saurabh Kundu, who is the Chief of Sustainability at Tata Steel, for having some conversations around the viability of hydrogen, because that is something that always comes in. While the technical feasibility is very important, it's also important to see at what point what should happen in order to establish some viability around utilizing hydrogen. So again, thanks to Dr. Saurabh Kundu as well. Now getting into the team members. So I've been the PI for this project, and Ram Prasad, who is going to run us through the steel insights. So he was the anchor around the steel side of things. While all of us have ventured into the steel, cement has also played an important role here. Now, the practicality of hydrogen being used in cement is a challenge, both for the industry and for the government. So, the specifics around that will be explained by Venkat, that is Venganathan here. Thirumalai NC, who is present here, he has been a reviewer one, plus he is also the sector head in our institution. Finally, Dr. Rajalakshmi, who is also earlier the part of ARCI, now she has been the reviewer, plus she has played an instrumental role in DST. So I would like to thank all the team members. Now, under the advisory, I think I've already spoken about Dr. Sanjay Chandra. So we also sought discussions from Dr. Max Amann. So he played a very key role in establishing world's first hydrogen-based DRI unit, that is hybrid. So he was a part of the project member there. So he helped us in formulating some of these ideas around how we can think about hydrogen incubation outside DRI as well. While DRI unit, it's fairly the knowledge around hydrogen use in DRI as a reducing agent is well established. When I say well established, academically, there are enough papers to back some of these findings and things of that nature. But having said that, in India, it's slowly picking up, and we hope that over the next 5 to 7 years, we'll start seeing more functioning outlets. Now, finally, for the cement work, so we consulted with Dr. S.B. Hegde. So he plays an important role in Dalmia's approach towards sustainability. Now, there is a slight pivot. I use the word towards sustainability as opposed to hydrogen per se. The specifics again, Venkat is going to run you through. But fundamentally, if you see, decarbonizing cement is more rewarding as opposed to changing the fuel structure as to what are the challenges around it. Yet there have been a couple of papers written, and there is one very small pilot that they are trying to build where hydrogen is used as a blending agent as opposed to a direct fuel. So the specifics around that again, Venkat is going to run you through. So this is fundamentally the team. Now all this we have been using hydrogen, and Jay also spoke about hydrogen and its use case. Yes, these are early days. We are at least 10 to 12 years away from realizing the real potential of hydrogen. We have seen the hype cycles around hydrogen multiple times. It's been there for almost 5 decades now, more than 5 decades as a topic of interest. But purely from its potential standpoint, it's been there for almost 5 years now. One of the key insight that got us to think in this direction is actually this graph. So everything around renewable energy that you see today across India fundamentally amounts to 18% of the impact that we consume from a consumable standpoint. If you see energy as a commodity of interest from a consumption standpoint, it accounts for 18%. However, if you see, about 80 to 82% of our energy needs comes from heat demand. That's basically thermal energy. And there, if you see, it's the usual suspects, the likes of coal, oil, and natural gas. And of course, when I say oil, it's the derivatives of oil. And at some point in time, we have locked most of our processes to use this for longer periods of time. So the unlocking aspect of it is going to take time, which is what Jay was again alluding to. And it's basically one step at a time, one effort at a time, one sector at a time. You're trying to decarbonize them. Now this gave us the opportunity to see perhaps using hydrogen as both fuel and feedstock. Now, what do I mean by feedstock? When it's used in a process as a reducing agent, not for its energy provision capabilities, but from a reactionary effort standpoint, that's basically feedstock. So hydrogen as a feedstock and fuel can unlock multiple levels of decarbonization opportunities for both, particularly for cement and steel. Now, energy from, so we have two different variables here, right? So one you have is energy, that is from in terms of how much energy is consumed by whom and things of the nature. So in that ranking, industry ranks second, obviously. Now then you have from an emission inventory standpoint. From an emission inventory standpoint, clearly it's the industry that comes second, and industry consumes more energy, most energy actually across India, right? So that gives us an opportunity to see sooner or later almost 60 to 70% of their energy requirements is thermal. So right away, if you see, it's not the percentage came, but it's actually the ability to substitute coal requirements and gas requirements slowly but steadily through concerted efforts around hydrogen. Now, in terms of our bigger commitment, obviously there is net zero, as Jay said. There is also the NDC goal, and you also have RE targets, that is renewable energy targets, that is climbing up. So given all this, the common denominator across all this, if you see, is a fuel that is scalable, a fuel that is reliable, and most importantly, a fuel that can use the efforts by other parameters. What do I mean by that? While National Green Hydrogen Mission as such is a good initiative, when you combine that with the initiatives floating around solar, obviously it's going to unlock an even bigger potential. So that's exactly the reason why we decided, all right, there is merit in going the green direction way. Obviously, we are not going to get, this is not hydrogen 101 in the sense, we are not going to discuss about the possibilities of blue hydrogen and things of that nature. While there is research underway around the efficacy of blue hydrogen, and gray hydrogen is anyway up and running, especially in refineries and fertilizers. So again, there is some market. By and large, if you see, hydrogen has been a captive market where the producers and consumers are same members basically, right? So once you break the captivity of the market, so then when new entrants come in, so that's going to again revolutionize the way the fuel is being consumed. So these are all the parameters that allowed us to think this is a right direction. It's a right direction moving forward. Plus, finally, before I give my baton to Ram Prasad, one of the key aspect here is the application of hydrogen in steel and to some extent in cement. It's well aware of within the industries, but the larger community and the information asymmetry that was floating around, let's say 3-4 years back, as to whether hydrogen can be used or not, we wanted to not debunk it per se, but throw some light into the sort of public diaspora as to what is possible. So that also was the one of the key reason as to why we embarked on this project. So now that the project is completed and our results have been fairly satisfactory when it comes to application of hydrogen directly, right? So right now the next step for us here is to get into the industry specific standardization. So as you may all know, the green steel taxonomy was released last week. It has created both positives and negative vibes per se around the functioning element of the taxonomy per se. While the intent is clear, is to greenify the sector, it's how we do it and what kind of boundaries we draw within themselves that calls for more discussions. So hopefully this session will allow us to think in what ways can it be changed, and simply speaking, whether hydrogen has a role to play there, right? So it's a starting point, as Jay said, just to culminate, it's a starting point. So now we are at least 5 to 7 years away in terms of seeing real results from the industries. So with that, I'll pass it on to Ram Prasad, and he'll run us through the insights from steel. Thanks.
Wishing you all a very warm welcome. India has a very rich tradition of iron metallurgy, with the iron pillar known for its unique rust-resistant composition, showcasing India's technology prowess. Now, India is second in the world in terms of crude steel production after China, employing close to 6 lakh people and contributing close to 2% of India's GDP. This is projected to grow with the National Steel Policies released in 2017, which aims at a production capacity of 300 million tons by 2030. The present crude steel capacity in India is around 180 million tons, with crude steel production at around 145 million tons. Let's look at the primary steel making routes in India. The two dominant methods are obviously the blast furnace, basic oxygen furnace route, and the DRI route, often paired with the electric arc furnaces. The BF-BOF route, which uses iron ore, coking coal and limestone, is the traditional method producing most of India's steel. However, it has a significant carbon footprint, emitting close to 2.5 tons of CO2 per ton of steel. On the other hand, DRI-EAF route is split into the coal-based and gas-based processes. India is the world's largest producer of DRI, with production of close to 52 million tons. The 82% of India's DRI is coal-based. The emission footprint in this route is close to 2.2 tons of CO2 per ton of crude steel in case of coal-based, and 1.3 to 1.8 tons of CO2 per ton of crude steel in case of gas-based DRI. As discussed in the previous slide, the material and resource requirement is depicted here. These are typical resource requirements with no particular bearing on the geography of the plants. This basically shows the energy intensive nature of close to 26 gigajoule of steel of the steel making sector and its inherent dependence on coal in the prevailing scenario. And therefore, this emphasizes the need for transitioning India's steel sector to lower emissions technologies. The scope of this work is on blast furnace iron making. The blast furnace is a typical equipment where iron ore is reduced to iron. The typical volume of blast furnaces is close to 5,500 meter cube in typical integrated steel plants. However, they come in variety of configurations. The major material streams, zones and reactions are listed here. We'll take a deeper look at the reactions in upcoming slides. The iron bearing material the flux and the coke is charged from the top of the furnace. The auxiliary reducing agent, which is ARA, and the hot blast is charged from the bottom of the blast furnace. The output streams are the top gas, slag, which contains the impurities, and the hot metal. The slag and hot metal is tapped from the bottom of the furnace. The hottest part of the furnace is the raceway, which is below which comes close to the bottom of the furnace, where the temperature of the gas is close to 2200 degrees Celsius. The temperature gradually reduces as we move up the furnace. The reactions in the furnace are detailed in the next slide. So the fundamental reactions in a blast furnace are the indirect reduction, which happens because of the carbon monoxide, the direct reduction, which happens because of the carbon in the blast furnace, and the upcoming hydrogen based reduction method. In the indirect reduction process, carbon monoxide produced from carbon sources reacts with hematite and magnetite in the higher zones of the furnace. This results in metallic iron and release of CO2. In direct reduction, which occurs at the hotter lower portions of the furnace, solid carbon from coke reduces iron oxides directly to metallic iron, also releasing CO2. With hydrogen reduction, hydrogen gas reacts with iron oxides to form metallic iron and water vapor instead of CO2. Together, these reactions highlight the current reliance on coke and CO while emphasizing the need to transition to hydrogen reduction. One point to highlight here is the reduction of FeO to Fe is carried out by competing reactions between the direct, indirect, and the hydrogen reactions at the bottom of the furnace. We look at some common decarbonization measures considering the dependence on coke, which makes steelmaking a hard-to-abate sector. Firstly, the energy efficiency, which is considered to be low-hanging fruit. By optimizing processes to meet the best available technologies or BATs, plants can achieve significant reduction in emissions. On the other end of the spectrum, we have techniques such as CCUS, which allow plants to directly remove the carbon generated in the process. Next, fuel substitution plays a critical role where alternative fuels such as biochar, methane, or hydrogen, which includes hydrogen-rich gases as well, can be used to lower the carbon intensity of production. Utilizing secondary steel or recycled steel is also a major lever for decarbonization here, as it primarily significantly reduces the need for primary production, which is far more energy and carbon intensive. The hydrogen use in DRI has seen sufficient academic attention and worldwide pilots. However, hydrogen use in blast furnace has seen trials in Tata Steel recently and companies worldwide. The scope of the study is to analyze the injection of hydrogen to a blast furnace in an Indian context. To carry out the analysis of hydrogen injection at 25 degrees, some boundary conditions have been assigned. The composition of the streams, namely the ore, sinter and pellet, and hot metal is fixed after consulting with industry experts and is assumed to be representative of the Indian feedstock. The ratio of sinter, pellet and ore is also corroborated from secondary literature and industry experts. Added to the earlier abbreviations, we also introduce abbreviations of RAFT and TGT, which are raceway, adiabatic flame temperature and the top gas temperature. And maintaining these temperatures is crucial for unhindered blast furnace operation. Based on these mass boundary conditions, a mass and energy balance of the blast furnace control volume was done. And we also analyzed the RAFT and TGT. To establish the veracity of these results, we've conducted validation and based on these validation checks, the model is deemed to be validated. Otherwise, the analysis was repeated. So this basically follows an iterative procedure to establish, to meet the boundary conditions as well as the constraints that I'll be explaining now. So in the model validation, basically, slag composition is used to gauge the veracity of the compositions and the material balance analysis. With slag basicity, weight fraction of the oxides of calcium, silicon and aluminum in slag as relevant parameters. In an Indian context, basicity of 0.95 to 1 is observed. Weight fraction of oxides of calcium, silicon and aluminum is greater than 94%. Alumina weight in the slag should be less than 20%. These all have technical importance. For example, alumina weight fraction directly is proportional to the viscosity of slag, and it's recommended that the viscosity is kept as low as possible, which is why alumina weight fraction is also an important parameter. When based on these analyses, the boundary conditions and the constraints set on the RAFT and TGT, we've arrived at the results of the hydrogen injection blast furnace, which has yielded interesting results. One of the key outcomes, as would be intuitive, is the reduction in coke consumption, as hydrogen acts as an additional reducing agent, improving overall carbon efficiency. This leads to a decrease in CO2 emissions by approximately 8 to 9% compared to conventional iron making process, conventional operations of blast furnace. We observe changes in the furnace temperature profiles as well because of the hydrogen endothermic reaction, which causes slight cooling effects, which required adjustments to the hot blast properties to maintain the thermal stability. Lastly, the impact on slag composition, equilibrium, and the final metal quality was carefully ensured such that the hydrogen injection does not affect operational requirements while reducing emissions. Some of these aspects of operational impact is also explained in the next slide. We see that as hydrogen injection increases, the utilization percentage, which is basically how much hydrogen actually participated in the reaction, in the reducing reaction, gradually decreased and plateaued at around 20 to 30 kg per ton of hot metal. Further, it is seen that the raft and top gas temperature dropping. However, this can be circumvented in some ways by enriching the oxygen in the hot blast. We've seen this is a general operational parameter. However, the analysis sees that a 2% enrichment increases hydrogen injection to 33 kg per ton of hot metal, with emissions again reduced to close to 9%. Injecting hydrogen has an interesting impact on the emissions as well, which has been done in multiple industries, including Nippon Steel. This result has been taken from Nippon Steel. We haven't done the analysis here. And it sees that higher temperature of hydrogen injection has the potential to reduce up to 22% of emissions. This injection of hydrogen at higher temperature again comes with its own technical challenges which warrant further analysis. The mass and energy balance relation across the blast furnace is depicted in a graphical manner known as the risk diagram. This is useful to analyze modifications in the blast furnace operations. The impact of hydrogen injection into the blast furnace is also shown here. The X and Y axis is basically the X-axis is the reduction efficiency. For example, if you have a reducing agent that goes in, how much of that reducing agent is converted to the oxide of that reducing agent, which is basically seen in the O by C or O by H2. The y-axis of the risk diagram is the oxygen that is brought into the blast furnace through iron bearing materials. The slope of the risk diagram basically denotes the quantum of reducing material inside the blast furnace per ton of hot metal or per ton of steel, per ton of iron. The y-intercept in the lower, on the negative y-axis, shows the oxygen content in the blast. This is important because we've seen as the hydrogen injection increases, the O2 requirement in blast is increasing. This may be explained due to the endothermicity that is brought upon because of hydrogen injection, which necessitates the use of oxygen, increased oxygen to the blast for efficient operation. Every intervention that we do has an economic impact. Let's delve into the economic analysis of the hydrogen injection into the blast furnace. One of the primary consideration is the cost of green hydrogen, which is directly linked to the price of renewable electricity. It is seen that the price of steel increased to the order of 39% on GH2 injection, assuming a cost of RE at 7 rupees. We have done a sensitivity analysis also from the price of renewable electricity for hydrogen from 4 rupees a unit to 14 rupees a unit. And the range that we've seen that the steel prices could increase is from 26% to 69% from conventional methods. Just as a disclaimer, I would also like to mention that hydrogen storage is an aspect that is not covered in this study, but we've heard from industry experts that it adds close to $2 to the base LCOH as well. As with any work, the work here also has some limitations. One issue that we observed is the slack content in operations in our study often falls below the industry benchmarks, where our analysis shows 305 kg per ton of hot metal, whereas 340 kg per ton of hot metal is in typical plants. To address this, we need access to plant level charge composition data that will actually accurately reflect real world operation conditions. Again, this study has been again the critical area is the difficulty in scaling up from pilot scale operations to full scale industrial setup. For instance, this study uses data for direct, indirect and hydrogen injection from a 12 meter cube blast furnace, which does not fully capture the flow patterns, heat distribution at the scale of actual industrial operation of 5500 meter cube. Finally, the economic evaluation, much of the data comes from secondary sources, which introduces some uncertainties. For example, generalized assumptions for fuel prices can distort cost analysis. Additionally, the variability in operation conditions across different plants can further complicate economic evaluations. We can improve the the analysis by actual plant level data, which will give a better degree of accuracy. From this study, we'll discuss the key policy levers needed to support the decarbonization of the steel sector. First is to enhance iron ore beneficiation to meet growing steel demand and improve the iron percentage in the charge to the blast furnace and or the DRI process. Further, as Murli alluded to, we had mentioned that a green steel taxonomy to standardize green steel definition would go a long way in establishing credible benchmarking systems. As luck would have it, the ministry has come up with a standard just 2 days back. We require some targeted policy interventions to reduce green hydrogen cost as well. To reduce the cost of green hydrogen, first we must create robust financial support mechanisms in form of low interest loans, for example. Public investments and carbon markets can help bridge the cost gaps for ensuring green steel production. By ensuring that these projects are financially viable, we can drive innovation and large scale adoption. Another crucial element is ensuring a low cost supply of renewable electricity. Targeting a cost of 2 rupees a unit would be a feasible number as per industry experts for viability of hydrogen in steam is what we understand, and this will require streamlining regulations, investing in grid infrastructure and securing long-term PPAs for making these green technologies more competitive. We further require long-term strategies to establish strategic infrastructure for hydrogen storage and its distribution. This will facilitate widespread adoption of hydrogen. Advanced market commitments will be essential in stimulating demand, reducing market uncertainty and enhancing R&D in the field. By using these AMCs, we can incentivize early investments and ensure a reliable market for green steel. Finally, the entire strategy could be supported by public-private partnerships and industrial collaborations. These partnerships will provide necessary resources, expertise and scale to drive these critical interventions forward. I will now call upon Venkat to explain the aspects of the results on cement sector. Thank you.
Thank you, Ram Prasad. Good morning, everyone. Similar to iron and steel, cement is yet another hard-to-abate sector that plays a crucial role in India's growth story now. We all know India is a construction powerhouse. Whether it's building homes, offices, highways or factories, cement is the backbone of all of it. In fact, India is the second largest cement producer in the world. That's right, just behind China. The numbers speaks for themselves. Our installed capacity and production are massive, and the demand is only going up. Why? Because our real estate infrastructure sectors consumes about a staggering 67% of cement demand, and housing alone basically contributes to this. But there is a flip side. The cement industry is energy intensive and contributes to emissions. Today, the sector has almost completely shifted to dry process, which is more sustainable, efficient, and uses less energy and water, and helps cut down on costs. In fact, the Indian cement sector is one of the most energy efficient in the world. Now let's take a quick look at the cement manufacturing process. It's a fascinating and intricate process that turns raw materials into the essential building block of construction. Now, if you look at it, we have the limestone, clay, and other components which are extracted from quarries, and these materials are sent to a crusher where they are broken down into smaller pieces. From there, the crushed raw material enters the vertical roller mill or VRM. This is the typical mill. There are also ball mills that are being used in some plants, but VRMs are far more efficient than ball mills. And this is where the material is finely grounded to about 90 micrometers or 90 microns into a uniform raw meal, and this is stored in raw meal silos. The next stage is heating, and this is where things get interesting. The raw meal is sent to a preheater and then to a pre-calciner, or they also call it a calciner, where high temperatures about 900 degrees are reached to achieve decarbonization of limestone, the reaction that you can see at the bottom. This reducing the energy usage inside the kiln. To assist this process, tertiary air and countercurrent hot gases also come into play, making the process more efficient. The material then moves into the rotary kiln, where it's heated to as high as 1400 degrees to form clinker, the key ingredient in cement, those small hard nodules. The hot clinker then passes through a great cooler, which rapidly cools it down to about 150 degrees Celsius. Once cooled, the clinker is stored in the clinker silo before heading into the final grinding process. At this stage, a roll press or a ball mill or even a VRM is used to mix clinker with other additives such as gypsum and even blast furnace slag to produce cement. The cement is then stored in a cement silo before being packaged and sent out for use. It's worth noting how important equipments like electrostatic precipitators is used in the process to ensure emissions and dust or other particulate matter is controlled. In short, cement production is a complex multi-step process that balances precision, energy, and sustainability to produce a product that powers the world around us. In India, the cement industry alone emits around 235,000 gigagrams of CO2 emissions annually. The emissions of this industry comes predominantly from the industrial process and product used, IPU category, or energy-based emissions. The biggest source of emissions come from decarbonization of limestone, and this particular process alone contributes to 56% of the total emissions. Next, we have emissions from thermal fuel requirements, which accounts for about 32%. This is primarily due to the energy intensive heating needed for the cement manufacturing process, as we discussed in the previous slide. And finally, the electricity consumption, which accounts for the scope 1 and scope 2 emissions of any cement plant process, contributes to about 12%. In earlier cement manufacturing processes, the kilns used were longer, and hence calcination also happened inside the rotary kiln. These systems were inefficient in terms of their heat transfer. So modern day cement making have a separate calciner where 90% of the decarbonation reaction happens, and these chambers alone consumes about 60 to 75% of the total fuel requirement. While it has been established that cement industry is emission intensive as well as energy intensive, over the years several decarbonization measures have also been developed. These measures can be bucketed as energy efficiency measures such as waste heat recovery, offering up to 10% emission reductions, alternative fuel and raw material resources that can be injected into the kiln, the use of renewable energy and green fuel in particular that can offer up to 32% emission reduction. Alternative materials such as clinker substitutes like fly ash, blast furnace slag also offer emission reduction up to 15%. As there is a minimum threshold for clinker factor for reduction, And finally, we have carbon management techniques such as molten carbonate fuel cells, calcium looping, and especially CCUS, which can offer up to 42% emission reduction. Apart from this, over time, electrification of cement manufacturing is also being explored, where electrochemical manufacturing techniques as well as novel techniques like Colebrook's rotodynamic heater are picking up, but these are at the very early stages, TRL 0 to 4 probably, so hopefully it picks up. When it comes to hydrogen utilization as a fuel in the cement making process, we have estimated that about 12 to 18 kgs of hydrogen for every ton of clinker can be injected into the pyro processing system, which is the rotary kiln and the calciner. And this can lead up to a theoretical emission reduction of 32%. Additionally, the use of low carbonate alternative fuels such as meat and bone meal, glycerin, and even paint sludge with their varying energy content has been evaluated across different cement types. By combining hydrogen injection with AFRs, fuel use can be optimized and emissions drastically reduced, paving way for a cleaner cement industry. The clinker factor is the ratio of the clinker, which is the key binding component in the cement, which is produced during the pyro processing, to the total cement that is being produced. Lower clinker factors reduce the carbon footprint of the cement, as clinker production is highly energy and emission intensive. Different types of cement have different clinker factors as tabulated below. For instance, ordinary Portland cement, the most widely used cement, which is used for construction of buildings, bridges, roads, etc., has the highest clinker factor, which can range from 0.9 to 0.95. Then you have the Portland Pozzolana cement, which is a blend of the ordinary Portland cement with materials like fly ash or even volcanic ash for up to 15 to 35%, and this offers higher resistance to chemical and attacks from sulfates and chlorides. So this Pozzolana PPC is best used in dams, marine structures, and sewage systems. Clinker factor for Portland slag cement, which is when instead of fly ash you use blast furnace slag or any slag per se, has a clinker factor of 0.68, which is not there, but Portland slag cement has a clinker factor of 0.68, and with a clinker factor of 0.55 we have composite cement, which has a clinker factor that can go up to 0.55. In fact, the minimum clinker factor should not generally go below 0.45 to 0.5. This is because to ensure adequate strength and durability is important. So there is a minimum threshold for the clinker factor as well, which should not go below 0.5. In addition to our theoretical estimation, there are journal papers. For instance, there is a journal that is titled Decarbonization of Cement Production and Electrification, where they used process simulation software like Aspen Plus to estimate hydrogen injection amount into the kiln. There are also multiple hydrogen-based trials reported, especially from Europe and the American region. To look at some of the real-world trials, we have Heidelberg Cement in Europe, where in a government-funded trial, they used a mix of hydrogen, meat and bone meal, and glycerin to achieve 100% replacement of the traditional fuel that was used. This proves that hydrogen can be combined with other alternative fuel and can fully substitute conventional energy sources. Then we have Tarmac from UK, where they conducted trials to replace their existing natural gas based rotary kilns to use hydrogen as an alternative fuel. You have Limak Cement from Turkey, where they conducted hydrogen injection and achieved 50% thermal substitution rates. And Cimex have been one of the forerunners in hydrogen injections, where they began their trials from as early as 2019, and then they have been expanding these trials to every global cement plants that they have, showcasing their leadership in hydrogen adoption. Then you have Argos that reported that injecting hydrogen and oxygen, they were able to increase their clinker output as well as reduce pet coke and their imported coke requirements. While this work marks significant progress, there are a few key challenges that needs to be fully addressed. Hydrogen combustion behaves differently from coal. It produces higher flame temperatures but less radiative heat. Unlike coal, it doesn't generate soot particles which enhance heat transfer. This could lead to uneven heating, and it could even potentially affect the quality of clinker that you are getting out. Also, there is limited literature around heat transfer models pertaining to hydrogen injection and rotary kiln. We also need a deeper understanding of hydrogen combustion byproducts. While we know water vapor is the main product, its interaction within the kiln environment and the effects of clinker properties remain unclear. Hydrogen's use may require a complete design overhaul of the kiln, which could also mean the need for retrofitment to prevent material embrittlement. Hydrogen being the smallest molecule, it can squeeze its way out of basically most of the metal that we have around today. And we also might need multi-channel burners, which might be necessary to basically adapt for the unique combustion dynamics that hydrogen offers. Addressing these issues is essential for optimizing hydrogen's role in clinker production and to ensure smooth transition to this hydrogen usage. That concludes our presentation. We are open to take any questions from the participants. Thank you.
We will now launch the report. I would like to invite Mr. Paramjeet Singh, Mr. Deependra Kashiva, Dr. Jay, Thiru and Murli to please come on stage to launch the report. Sorry. We now move on to the panel discussion part of it. As I mentioned earlier, we will be combining the two panel discussions. So the discussion topics today are challenges and opportunities for hydrogen incubation in the steel industry, as well as long-term perspectives of the hydrogen economy, specifically with regard to electrolyzers and fuel cells. I would like to invite the panelists on stage. Mr. Paramjeet Singh, Director of the National Institute of Secondary Steel Technology. He has more than 35 years of experience in the steel sector and has also worked with the Ministry of Steel in various capacities and has been a member in committees that drive steel decarbonization. Welcome, sir. Mr. Deependra Kashiva is the Director General of the Sponge Iron Manufacturers Association. He has played an instrumental role in addressing practical solutions for sponge iron manufacturing in various fora. Welcome, sir. Mr. Naveen Alawat is the head of Power to X Green Hydrogen, Green Steel Gasification Projects and CCU at Jindal Steel and Power Limited. With more than 13 years of experience in various fields of manufacturing of specialty chemicals, coal gasification projects and integrated steel plants, Mr. Alawat was also a member in the executive team which put up the world's first coal gasification based DRI plant in Angul, Odisha. He holds an MBA degree from IIM Calcutta. Mr. Alawat is joining online. Mr. Sujan Hazra, Principal Researcher R&D at Tata Steel. Before Tata Steel, he worked at L&T Technology Cell and SR. In his current capacity, he conducts research in blast furnace, iron making, process value chain analysis, evaluating alternate iron making, amongst others. He holds a master's degree in metallurgical engineering from IIT Bombay. Also joining online. Dr. R. Balaji, Senior Scientist, Center for Fuel Cell Technology, ARCI. Dr. Balaji holds a PhD from CECRI and has been working as a Senior Scientist at the Center for Fuel Cell Technology in ARCI. He has been published extensively in various international journals and has been a leader in technology know-how development across fuel cell applications. Welcome, sir. Mr. Anil Srikar Pavaluri, Head of Business Development, Greenedge Electrolysis. Mr. Anil is heading Business Development at Greenedge Electrolysis currently. After spending over 7 years in Thermal Systems Private Limited and L&T Power, Mr. Pavaluri has led the Business Development Unit in Toshiba JSW Power Systems for over 8 years. Welcome, sir. I now invite the moderators. The panel will be jointly moderated by Murli and by Mr. Thiru. Over to you guys.
Thanks, Malin. Hydrogen is a very challenging topic. Equally challenging is bringing these experts together on a timely fashion. So I think Mr. Naveen Alawat has managed to join in, but I think he's busy. So whenever he's available, he'll unmute himself and he'll talk. Last minute, yet another wicket. So we have Mr. Sujan Hazra, who has been roped into one of those usual meetings in Tata Steel, so he misses out. So what we'll try to do is, given the complexity of the topic, we'll make the session less complex by probably going in tandem. So I have 2 or 3 very, very key relevant question given the current situation. So the concept of individual net zero and things of that nature, let it lie on table, and probably that will allow us to publish the second report as well. While we keep that at bay, right now we'll focus more on 3 key areas in steel making. First and foremost is the recently released green taxonomy, the probability, or rather the possibility of green taxonomy revising over the next 6 months to 1 year. It is very, very rather, it's a blessing in disguise for us, for Mr. Paramjit Singh to be here, because NIST has been entrusted to oversee the quality, if I'm not mistaken, and the process of what qualifies as green steel and things of that nature. So he is going to probably, if I may request him as the first question, to introduce us officially to green steel taxonomy and probably speak a little about the intricacies around that, the process that was duly followed to get there. Because, sir, I also assume that you have more than 30 years of experience in the steel economy. Some of us, or rather I am that old, but Venkat here is not even that old. So your insights are going to be very, 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 very useful for us as we move to the next phase of this project. And number 2, that's the first question, the process of culmination around the green steel taxonomy. The need, we are fairly aware of it. Number 2, again, one of the hotly contested topic recently within the steel segment is CBAM. While Europe has its own version of CBAM, and there has been enough news outlets or murmurs around India wanting to get into that space, and the operationalization of CBAM per se, none of us are exposed to the intricacies around that. Now, what I want to hear is more from challenger standpoint. We don't need the specifics because we understand how sensitive a topic that can be. But what we want is, in terms of bringing industries together, because it has to be arrived based on a huge committee of performers, operators, and coming together, understanding, agreeing with a value, and then all the more reason for Ministry of External Affairs to again have their say on how to enforce it and things of that nature. So if you can spend some time on CBAM as well. And finally, from a ranking standpoint, we understand the notion of carbon capture and storage as a commodity, let's say today. Again, that has been a topic of severe contest in India, especially where iron and steel still has some way to go when it comes to maximizing the capability of energy efficiency. Then you have alternative fuels playing its due role, yet there has been something less scalable around. When as Naveen sir also joined us, so he may be able to shed some light on CCUS and green steel from Jindal Steel and Power standpoint. So he is going to talk. So instead of keeping it question and answer based, these are the 3 key pillars. If each of us could spend some time, let's say 5 to 7 minutes, even more than that, we are always welcome. So if you can just spend some time around that, and then we can have a open, if there are any questions, then some of these questions, some of the other pressing questions can be addressed around that. So Paramjit Singh sir, if you can start.
Thank you, Murli. Thank you so much. I think let us start from the way our industry works actually. So if we see that our sector, our steel is divided into two type of processes. One is the blast furnace route, other is the, you can say, DRI route. So both the processes are totally different. And if we see our processes from the global, you can say, based of, you can say, steel making, they have availability of scrap, and we don't have the availability of scrap, and we don't have the natural gas availability also. So we have many constraints in that case. And regarding the green steel taxonomy, which is being, you can say, recently floated by the Ministry of Steel, I think that will give a push to the industry. It will give a positive push to the industry, that because once you will standardize that 5-star, 3-star, 4-star, that will give a push to adopt different type of technologies. I think that is a very positive step by the ministry, and ultimately it has been now taken over to the pattern of the finished steel. And I think because of that, because whenever we are going to sell our product in the market, that is a finished product, not the crude steel. That is the basic concept behind it. And by you can say these measures of green taxonomy, the industry will now think of adopting different type of technologies where they were not focusing right now. And I think now the program what you have here today, you can say, is organized. It will also give the push to the use of different type of fuels, because right now we are mainly focusing on the coal, or you can say carbon. And by these you can say green taxonomy, it will give a push that the people will think about how they will use the different type of fuels. Like we have the options, like in DRI making, people can think of replacing coal with the biochar, and that will be carbon neutral, and that will again further reduce the, you can say, help to reduce the emission level and help them to come under the category of, you can say, type of green that taxonomy categories 3, 4, or 5. And it will also give the push to the to think that how we can introduce hydrogen in our processes. As you have, I think I missed the, you can say, presentation in the morning session, but I could make out that there was more of the discussion on the blast furnace, if I'm not wrong. Though in blast furnace we have very limited scope of use of hydrogen because of the certain, you can say, process constraints. But in DRI making, definitely there is a scope, because we already partly we are using in our country, people are using the gas based DRI. So wherever the gas being used, it can be replaced by the hydrogen, but the further constraint is that availability of the hydrogen and the cost of hydrogen. So if these constraints can be, you can say, overruled, or you can say that availability of the hydrogen can be made available at the low cost and easily available to the plants, because investing on hydrogen, it's again a capital intensive. So the industry would like to rather work on availability of the hydrogen rather than putting the you can say electrolyzers or the production of hydrogen. So if these type of things can be made available, that will help the industry to go towards that. And third is that now the industry will think of using more of scrap also, because that is also going to help them to reduce the emission level. Because earlier people were not if you see that in BF route, the use of that scrap was 8 to 10%. Now I think that where the globally people are using up to 25 to 35%. So it will give a push to the industry to use more of scrap to reduce their emission level. So there are many ways where we can think of to, you can say, meet the requirement of the green taxonomy. And I think in this, I think I would like to hear from the Kashivaji also. I think he can compliment on this.
I would like to supplement what my great friend has said. Your question was very specific about the taxonomy of the green steel. Ministry has very clearly defined now, I think the first time in the world, IEA or World Steel Association or other organization in the world has not come out with a clear definition of what is the green steel. It is first time that India has come out how they are going to define the green steel. For green steel, they have shown that one graph where at the bottom is a zero CO2, and threshold limit is the 2.2. And if the CO2 emission of a company is in between to that one, that the difference of that one is the greenness of steel. And if it is beyond the threshold limit, then they will be penalized. They have to buy the green certificates. So that is how they have defined. But the issue is, which I think Mr. Alawat will also come out, industry is little bit anxious because earlier the Ministry of Steel was defining everything in terms of the crude steel. But now they have come out in this recently held presentation in the Vigyan Bhavan, they are now talking about the finished steel. As per my information, all the major steel producers has come out with their targets in terms of crude steel. Say, for example, Mr. Alawat, I think his company has said that they will be achieving 1.84 by 2030. JSW said 1.8 by 2030. And Tata Steel also said, I will achieve less than the threshold limit. Mr. Hazra will say, I don't remember now what they have said, but all are below the threshold limit of 2.2 ton of crude steel. But the government have started talking of the finished steel. I wonder how they are going to revise their targets. I think the panelists would like to throw the light on that one. As regard to your second question about the CBAM, nothing is sure. If you read the various statement of our commerce minister, they have not accepted this concept. They as per the latest report, they will find in the WTO about this. But as far as we are concerned, we have got a CCTS scheme, carbon credit trading scheme, that is equivalent to the CBAM. And earlier the threshold limit was 2.54 of the CO2, but now this has been by ministry has increased to 2.64 ton of CO2. But this is going to be implemented after the 2029 to 30. So the problems will start in the 2030-31. So we have got a sufficient time. Main producer will take care of that. I am sure they will take care of, barring the sale, because one of the meeting which I was attending when the threshold limit is being, I'm not criticizing, I don't know this, the sale representative is attending. In that meeting, when we were debating about the threshold limit, and everyone accepted 2.2, but the sales representative said it should be increased to the 2.32 ton of CO2 per ton of CS. But I believe SAIL has also started taking the action. Say, for example, in their one of the integrated steel plants, World Bank has come forward. They are working along the TERI, preparing the report for how to produce, what will be the financial implication, and what will be the reduction of the CO2, what should be the process route. But SAIL have started taking the action fortunately. But my worries is, as Mr. Rampasha said, 2.2 ton, but that is the, and he said 2.2 ton per ton of the crude steel, whereas my information, I've got one of the best operating coal-based DRI plant, Mr. Godavari, say, and is how much is your CO2 per ton of DRI? How much is your? See, so that is the difference. Like the Tata Steel long product. See the thing. But most of them, since they have started the waste heat recovery based this power plant, they are able to reduce their energy consumption, specific energy consumption by 20 to 25%. And as per the BE report, we have got around 339 coal-based operating units Out of that, 142 have already installed the WHRV based power plants. So they will not face any problem to as far as to meet the norms per ton of the DRI. But they are definitely going to face a lot of the problem when we talk about per ton of the finished steel. But I'm sure a lot of the efforts are being made. CMI has taken a lead. Some 3 R&D projects the Ministry of Steel has approved to reduce to substitute part of coal by the different type of gases, say for biogas, say for example green hydrogen, say for example natural gas. But as in your presentation has come out, infrastructure of green hydrogen or biogas are very, very important. I've got around 10 members who has got a capacity of more than 1.5 million ton of coal-based DRI and finished steel. So these are the people who can afford, who have got the financial muscles to transfer from the coal-based to the gas-based. But it should be available at their gate or near their premises or in the cluster. So I have been fighting. I am very happy that you have also brought out that issue in your report. Thank you very much. If any other question, I will be happy to respond.
I think one point I would like to say that as Godavari has already, that Kashwari has told that 1.9 per ton of the DRI, by using the renewable energy in the melting, I think they can, you can say, come in the band of the green steel taxonomy. So yeah, I think it will also give a push to the use of more of renewable energy in the melting or in the steel making or rolling side, and help the industry to get the maximum benefit of taxonomy.
I forgot to mention that one. As per the BE norms under the PAT scheme, they have shown if you use the 100% scrap in the EF or IF, the CO2 emission is 0.55 to 0.65. And if you add that one to 1.9 or say 2.2, what you people have said, and if you reduce the thermal energy by the RE, they will come within that frame. So they are not scared. That is why today a very big capacity, individual capacity, coal-based capacity are being installed in the country in spite of that danda.
Mr. Naveen, if you would like to go now. The speaker. Yeah.
No, thank you. Am I audible?
Yes.
Yeah. No, thank you so much. Thanks. Nice. Actually, sorry, I couldn't actually come personally to attend this thing because of back-to-back meeting. But happy to be connected, and I think great points by Paramjit ji and Kishwaji. So a couple of points from my side and from the company. Basically, I'm representing Jindal Steel Power. So I think this CBAM, or the definition of green steel, that or the percentage of greenness, and that has been announced a couple of days back by Ministry of Steel. I think it's a welcome step, and I 200% agree with Kishwaji that first time in the world, at least the numbers, the definition is much more simpler, easy to understand, and this is a step in the right direction. The second point is that though this is a step in the right direction, there are some calibration. There are some, I think, navigation that need to be done on this. One of the things that we all have to sort of get our act together, and where we have to sort of collaborate and coordinate with the ministry, is about the emissions, the CO2 emissions per ton of crude steel. The definition has to be aligned. Though we have a very concrete definition, but the terminology, the nomenclature has to be aligned with the global standard. It is super important, right? We cannot have the different definition. Already so many definitions are there. We have to again start battling with the different technologies, and that is where it will confuse us as the steelmaker, and then of course the customers. At the end of the day, all these things are happening because there is a demand that is going to come from customer. There is also the willingness to pay that will come from the customer. If if we'll keep a very simpler things and a very easy executable strategy, then only we'll be able to serve the customer. Otherwise, customer will be super confused, and he is the one who is going to finally cut the check, right? Not us, right? That is very important. The third point is about the different strategies that I think most of the steelmakers are going to follow. The first and the easiest quick win, as I always say, it is about operational efficiency and energy efficiency. So operational efficiency, it is about how we can maximize the use of pellets, how we can integrate our process, how we can bring digitalization into the process, and all these things. I think most of the companies, they are doing it, right? So nothing new in this. Second one is about the energy efficiency, and to that, I think the biggest domino is going to be the renewable energy uses. I think this is going to be the biggest domino, and this lever, not all the companies across the globe, steelmaker across the globe, they have this lever. But fortunately, in India, for Indian steelmaker, this is going to be one of the biggest domino that we'll have. And this, why we are saying, you can see the penetration that is there. You see the overall basically the uses of renewable energy in the grid right now, it stands around 43%, right? So total capacity, renewable capacity in the grid right now is 213 gigawatt that we have already achieved, right? Our target is to achieve 500 gigawatt by 2030. So when we hit this 500 gigawatt, our grid, which has a carbon intensity right now at 700 kgs of CO2 per kilowatt or kilowatt hour, or 0.7 tons of CO2 per megawatt hour, I think that will come drastically down. That will come around 450 to 500. That itself will be, see the reduction of close to 15-20%, and that will be reflected in our steel operation as well. If I am 100% dependent on grid, if I am augmenting my capacity, renewable capacity on a standalone basis for a capital requirement, so that itself, that is an add-on. So all in all, what we are talking about, that renewable energy can definitely help us to support at least 15 to 20% in reduction of our carbon intensity, and that is the biggest lever for us. The next lever that we have is the biochar, biomass or biocoal. That is also one of the steps that can really help us, though it is not going to move the needle much, but definitely its addition in the electric arc furnace will definitely support us. It is one of the enabler. It is not a silver bullet that if we do this, then it will reduce the intensity, but it is one of the lever that we have. The issue on the biochar, it is about the availability of the biomass and the landed price of biochar. Now we have done the calculation, we have done the trial as well, though the Ministry of Power has already mandated to use 5% biochar pellets or bio pellets in the power plants. It is already being utilized, but the biggest issue is that how we can use it in our electric arc furnace, having the landed price. There has to be economics here, but right now the economics is where, because of the low density of biochar, the availability is a biggest issue, and right now the landed price is almost 30 to 40% higher than the coal. So it has to match with that. It has to the industry has to mature. Right now it is highly unorganized, but I think as we move forward, it can also be though the technology is very simple, it is a pyrolysis process. It is not a very difficult technology to have, but the availability of the biomass is the issue. Second, the quality of the biomass, that is also super important. Some of the biomass rice husk that we take, it has got a very high silica content. So that will also increase my slag percentage as we move down for the process. So we have to find the right quality of the slag, right quality of the biomass that can be processed. The next point is about the hydrogen. I think hydrogen at this point of time, it is not economically feasible, in terms of the levelized cost of hydrogen or delivered price. But I think the biggest domino that can really help us to drive down the price, the levelized cost of hydrogen, it is the electricity only. So right now, if we talk about the recently announced bid, that have been the lowest bidders, or they have won the bid in SECI. I think the round the clock 4 hours of storage, I think it has already hit 3 rupees 75 paisa, which is actually incredible. So as we move forward, the moment we start hitting round the clock, if we take the round the clock electricity in India at this point of time, it is close to 4.5 to 5 rupees. So that is round the clock, 24 hours renewable electricity. And that is where I think is the biggest impediment at this point of time. The moment it will start coming from 4.5 to 3.5 to 3 rupees, then I think we will be in a very sweet spot to drive down the levelized cost of hydrogen. The moment it will come between 1.5 to $2 per kg, right, most of the steel makers, they'll start using it, because that will make it will start making strength, it will start making sense. And at that point of time, the carbon credit market plus the willingness to pay by the customer, that will become very, very important. So I think as we move forward, the willingness to pay will come in India. Right now it is absolutely not there, and willingness to pay can only come when we will set the carbon prices, right? The last point on the CBAM side, I think it is, I strongly believe it is definitely, though the Ministry of Steel, along with our government of India, I think they are fighting this point at the WTO level, that yes, it is a tariff barrier, and the developed countries have to definitely support the developing countries. They have to give them an adequate financial push to really adopt all these technologies. But I think with our way of working, with the Indian way of working, I think it give a very, very important opportunity, very incredible opportunity for all the steelmakers in India. So I think more and more things will become clear. Even CBAM itself, it is not clear about the countries in European Union. They themselves are not united. But I think as we move forward, things will become more clear. But I think it will be at a broader level. I think it is going to give a very important, opportunity for India, because of the simple fact that in European context, if you see, the steel makers are going away from Europe. You see, ArcelorMittal, they have clearly said that yes, I think because of the demand, because of the operating, enablers, they are more or less moving away from Europe. Liberty Steel is also sort of in doldrums. So I think the Indian steel makers, it is very clear the steel making thing is moving. It is shifting away from Europe to Asian countries, China and India. I think this is where we are going to amazing opportunity for us. By 2030, there will be close to 50 million ton of low carbon emission green steel demand in Europe. And if we take all the announced capacities in Europe, they won't be able to go beyond 10 to 12 million ton or 15 million ton. So there is a very good upside of close to 35 million ton. And if India can take only 50% of that, so that is like close to 17 to 80 million ton. So that is where I think the opportunity is. So I think very important thing as we move forward, it will also, maybe it may not come from 2026, maybe from 2030, but it start giving us that basically we'll start warming up ourselves to how to become from good to great. So I think that warming up, that practice, I think is super important for us to really take it forward. The last point is about our company. I think we are seized to this fact that operational efficiency, energy efficiency is absolutely the low hanging fruit for us, and we have already started basically commissioning the uses of the pellet plant. We have recently commissioned 6 million ton rotary kiln pellet plant in Angul at our facility, and we are going to augment the similar capacity in Angul, going for another 6 million ton plant. And by starting using the iron ore pellets, it increased the productivity of our DRI kiln by 15 to 20%. It's so super important to have this pellet. So that is the low hanging fruit that we have already capitalized. The second is about the deployment of the slurry pipeline from Birdville to our Angul. So that is also one of the project that is almost completed. Another 40 odd kilometers pipeline we have to lay. And we are also integrating all our mines, coal mines with our plant by having a pipe conveyor. So that will also help us to reduce our scope 3 emissions. So all this integration plus digitalization, uses of the off gases, valorization of the off gases into important chemicals like ethanol, methanol. These are one of the things that we are absolutely in a very advanced stage. And in next 4 to 5 months, we see a lot of things happening where the firm contracts we are going to sign off to start deploying these technologies. The next point is about the hydrogen. As I said, though the hydrogen is coming at a premium at this point of time, but we have to start learning. We have to start deploying it. We have to start seeing a lot of learning points, data points that we need to create, between the electrolyzer to renewable energy and then the hydrogen with our DRI furnace. So we are putting up India's biggest electrolyzer capacity of 30 megawatt by end of next year. We are going to place the order within the next 1.5 months, and by end of next year, we by this time we are going to commission this 30 megawatt electrolyzer. So the capacity will be around close to 13 tons of hydrogen per day, and then this hydrogen we are going to blend in our DRI furnace along with the synthesis gas that we are using in one of the furnace. So this blending is like close to 55% of the overall blending, but this will give us enough data points to how we can augment it. So this is the final thing that we are doing, apart from adding gasifiers, how we can basically do the washing of the coal, how we can sort of valorize it, reduce the carbon intensity. One of my friend in Godavari, he said 1.9 tons of CO2, but if I see washery and coal gasification to DRI plant, our plant has got 1.45 to 1.5 tons because of the clean gas. So I think there is, as Paramjit ji has rightly said, I think there is a tremendous upside so far as the DRI making is concerned, because you can use the renewable energy there, electric arc furnace, which consumes close to 550 units per ton of steel. If you can think of, basically adding 50% of renewable energy or completely renewable energy, you will go you can reduce close to 550 to 600 kilos of electricity, CO2 intensity by using renewable energy. So there is so much of upside, and everybody is seized to this fact, and everybody is learning. And I think we have to see this as an opportunity than as a basically a one-sided push. But I think it is definitely an opportunity which we all have to seize, and everything is going, I think, in terms of the learning curve, in terms of the overall technology selection. I think India is absolutely at a sweet spot, and we as a steelmaker, I think, can really, I think, take this legacy forward. We can be. This is the amazing opportunity. We were never in the forefront of the overall technology in terms of low carbon emission steel, but now I think we can seize this opportunity to be at the front line. Thank you so much.
Thanks, Mr. Naveen. Thanks for sharing inputs. And as you rightly talked about, yes, hydrogen is something that we need to take forward, and we need to learn, and we need to build. So in order to talk about hydrogen and electrolyzers, we have people from ARCI, Dr. Balaji, who is here, who can throw us more light on what's happening in this space. But before talking about getting into this hydrogen aspect, one has to understand we have set a target of around 5 million tons by 2030. That means we have to add around 1 million ton in the next 5 years. And for every ton of green hydrogen that we want to produce, we are looking at around 20 to 30 gigawatts of RE power that is being added. And now beyond 2030, we need to add around a rate of 1.5 million tons per annum, considering a target of around 30 million tons. Now, two aspects has to be looked into. One is, where do we create the demand? Now, as we have looked at it, steel is still growing, and still it's looking for how much blending can actually be done and whatnot. But definitely there are other areas, and I think we have the right panelists in this. Mr. Anil also from Greenwich Electrolyzers can throw us more light on various application areas. So for hydrogen to grow, we need innovation in terms of the whole electrolyzer, fuel cells and whatnot in the next 2 decades. We also need to have a huge infrastructure not in just terms of the hydrogen pipelines, but also we need from the RE. People talked about we need to more blend or add more RE into the system. So there is a huge opportunity, that's it. And finally, it's the investments that has to happen. There's investment not just on the hydrogen side, but everywhere. RE plus also on the hydrogen equipment manufacturing, hydrogen production, and transportation and utilization at the end. So investments has to happen across all these three. So to begin with, I'll start with Dr. Balaji. If you can throw us some light on the role of these materials, advanced materials, in enabling this long-term deployment of fuel cells in the hard-to-abate sectors. What is happening in this space, and tell us more what you have been doing in ARCI.
Yeah.
Thank you.
Thank you for invitations, and I'm happy to be a part of this event. As you rightly mentioned that the most of the hydrogen cost is coming from the operational, energy consumption for the hydrogen production actually. So if you see this recent IRENE report, the set target for achieving the lower cost of the hydrogen. So the thrust area of materials is in terms of even if you see the commercialized alkaline water electrolyzer or PEM. These are the two technology which is being widely commercialized actually. So the main research area where we want to focus is the kind of separator material as well as the membrane. So these two area will occupy more of the cost of the system actually. So right now, this if you take the PEM based system, which are fluorinated polymer backbone. So in India, we don't have a much fluorinated except the Gujarat fluorocarbons actually. So concentrating on more on development of separator gas separator material, which is used for alkaline water electrolyzer, and in the case of PEM, the membrane actually. So these two area where we need to concentrate more, and also in material aspects, once we start deploying this electrolyzer technology for various applications, it is a right time to think about the recycling of the materials actually. So these two aspects, I mean, because we use some noble metal in case of PEM, and it's non-noble, that's nickel also, is a very expensive. I mean, so we need to think about that end of the electrolyzer, right, how we can reuse the materials for same for hydrogen applications. And ARC also is working on this recycling aspects of this component, especially for the membrane and separator and this electrocatalyst material. So the recycling of the material which is being used in the electrolyzer manufacturing and the membrane and separators, actually these two area where we need to more focus on indigenous development as well as the attempt to reduce the cost. And finally, one more area where we need to concentrate right now. So India has the chloralkali plant, which is largest amount of hydrogen byproduct actually. So and here the chlorine consumption when compared with Europe and other, I mean Europe, US concern, the per capita chlorine consumption in India is very low when compared with other things. So I mean the demand side, if you said the demand side, if you want to increase the hydrogen, so the chloralkali, more number of chloralkali industries, because they are using PEM membrane based electrolysis process, and they use three different byproducts: hydrogen, chlorine and NaOH. These are all value addition. So make the byproduct also scale valuable and cost effective, so that the hydrogen cost will also come down, and which will leads to the hydrogen easy adoption for various sectors actually.
Also, you did work on some on the telecom towers to look at basically diesel abatement in telecom towers using hydrogen fuel cells, I believe. So if you can throw some light on it, what was the project about, and what was the initial results seen in that space?
I think it's a good start for adoption of fuel cell technology for a backup power application actually. So I think Geo has already carrying out the field trials, which they are implementing about 150 towers, which is being powered by fuel cell actually. And the study shows that actually, which is also cost effective on par with the diesel generator. Only thing is they do the hydrogen generation on site by reformer, actually chemical reformer of methanol, so that they produce on site hydrogen generation, and which is being widely used for the fuel cell application. And right now ARC is also engaging in this project actually by conducting field trials. So because we have a electrochemical reformer which will produce hydrogen at the same rate of chemical reformer, and which can be easily integrated with the renewable energy sources actually. So the electrochemical or methanol reformer or chemical reformer on-site hydrogen generation, which will couple with the fuel cell. I think this cost economics also worked out actually based on the Geo experience is that it is on par with the diesel genset, and the carbon footprint has reduced tremendously when compared with the diesel genset. And in terms of maintenance also is very less in the case of fuel cell and chemical reformer combined when compared with diesel genset. And there are some practical difficulties when you do the diesel generation as a backup power for telecom. So every 3 hours, 4 hours, it has to automatically go to shutdown to maintain some kind of temperature. So during that time, they use the battery as a power pack, and after 3 hours again they have to restart the engine, I mean diesel generator. So that kind of limitations can be overcome by the fuel cell, as long as you have a fuel in terms of methanol, if it is 30-70 ratio with water, and as long as you have a fuel, you can continually without non-stopping you can run the fuel cell, and it can meet out the demand for the telecom tower. And apart from the methanol, actually now India is looking for more ethanol based things actually. So, and we, as I said, we develop a electrochemical reformer to generate hydrogen from methanol, and the same system can also work for ethanol. So whether it is methanol or ethanol, the emission CO2 emission per kg of hydrogen is same, because the stoichiometric equation, if you see, then the emission of CO2 will remain constant. So now the ethanol is more in India availability when compared with methanol, and we can also look about the ethanol based hydrogen generation system on site, which can be, because these are a membrane based system, and which will yield more pure hydrogen, which can directly use it for the fuel cell application. I think this telecom tower is a starting point for implementation of fuel cell with the commercial market.
Okay. Mr. Anil, you've been working on the whole PEM and in PEM thing, technologies. And despite having the advantage of PEM and RE compatibility, there seems to be a positive outlook also on both alkaline and solid oxide based solutions. How is GreenH positioned to take this forward?
Yeah, coming to outlook on the alkaline technology, if you see, the market is always positive towards alkaline. It's a mature technology, around more than 100 years old, and we have a stack sizes of 2.5, 5 megawatt, 7 megawatt. So recently what Mr. Naveen was saying, for 30 megawatt one, that would also be on alkaline technology. So industry, it's a well-known technology. I mean, it's a matured one. Only thing, it's low on capex as well to initially start with, and to prove of 80,000 hours of operating hours and all. Alkaline technology is having the number of years of operation as well. Only thing is that in that alkaline technology, the OPEX costs are quite high. I mean, there is electrolyte replacement, cell stack replacement, refurbishment and all, which would make the levelized cost of hydrogen a little bit higher. And ultimately, it boils down to the cost of the power. So the power cost which is given to the alkaline technology, if it is at lower, then obviously the cost of hydrogen would be lower. So the market is always positive towards alkaline technology. It's a matured one. If you see the results which are coming out in the SECI tenders for the electrolyzer manufacturing and all, many of them are planning to set up the alkaline manufacturing in India as the first one. Compared to PEM, we can see only the 1 or 2 guys in the market. But alkaline is what everybody is banking upon because of its lower capex. But we need to have some kind of data points, how it is going to operate with respect to its compatibility towards RE. If we have a stable source of energy with a CEO of like 80%, 90%, definitely alkaline is the best bet technology. Its startup times are very slow. I mean, it operates between 30 or 40 to 50% to 100% of turn-down ratios. If that is the case, then you need to have a stable load of energy. And that to achieve in renewable energy would be difficult because there are fluctuations anytime. If there are certain fluctuations, again, it has to start from scratch. So people have to they need to understand about these data points as well, how it has to be integrated with renewable energy. That is what exactly is green hydrogen. It can operate on grid, then it is not green, first of all. And that grid, we don't know, right? It's a green or anything. So outlook on alkaline is more of a positive thing right now because of the capex part. But OPEX, people need to still understand what exactly, how it is going to operate with respect to the renewable energy. And coming to solid oxide, which you are asking, we ourselves, I mean, we have a JV with a parent company H2B2. So we are manufacturing SOEC electrolyzers. It's a high temperature electrolysis technology. Like it's a specific applications would be in steel plants. We have this ammonia synthesis plant because it uses high temperature steam at 780, 800 degrees centigrade. So the amount of energy which is to be incorporated to split the molecule is quite less in SOEC technology. So it has specific applications specifically in steel or cement or synthesis plants, ammonia synthesis plants, wherever you have a lot of waste heat. And waste steam can be used directly in SOEC technology, and that will reduce your power consumptions more than 30 to 40% compared to alkaline or PEM. And its efficiencies are upwards of 80%, 85%, 86% and all. But the problem is the stack sizes are only 10 kilowatt stack size, and you make an electrolyzer of an 1 megawatt or an 2 megawatt combining all the stack sizes. So that is going to take some time. In order to achieve 1 megawatt stack size in SOEC, it's going to take more than 10 years of time. And we are doing right now on 10 kilowatt stack. So alkaline right now, alkaline and PEM, these are the most mature technologies which people are banking upon. And SOEC is the other future technologies. And there is another technology that is anion exchange membrane, that is AEM. It is similar to alkaline, but it's a membrane technology. Again, here it's the membrane as a problem. The ion conductivity of the membrane is quite slow compared to PEM, because of which its current densities are much lesser, and because of which the efficiencies are lesser. Again, R&D is going on in the membrane technology of the AEM part. Its capex is lesser, its OPEX also would be lesser. It is having advantages of both PEM as well as alkaline. So this technology would be a groundbreaking technology in the future. It can try to replace both PEM as well as alkaline.
Greenedge also have to have embarked on an interesting application, that is use of hydrogen in trains. Can you talk us through that? What you have been company doing in this space?
Yes, this is one of the most ambitious project which Indian government has taken forward. We are actually setting up India's largest refueling station, around 420 kgs per day, to fuel India's first hydrogen train developed by Indian Railways. The plant is in Jind, Haryana. So it's an 1 megawatt PEM electrolyzer which we are making in our factory, and it produces around 430 kgs of hydrogen per day. And it also includes compressing up to 500 bar and storage of 3000 kgs on ground in high pressure storage. We have both 200 bar as well as 500 bar. And in type 1 and type 4 cylinders. I'm sorry, I'm going slow a little bit into technical part. And we have dispensers located 210 meters away, 2 dispensers. So this is India's first hydrogen train, and happens to be the world's largest hydrogen train, running around 400 kilometers daily, and it will consume around 420 kgs per day. So we are setting up the hydrogen refilling station for it. The plant is going to be commissioned by next month, and we are dispensing daily 420 kgs into the train. It will run around 400 kilometers the train, and it will travel around 400 kilometers. So per kg around 1 kilometer is the average the train will consume. So Railways is taking up this project as a pilot project, and the success of this particular project they're studying, to have these applications not only in passenger trains but other trains as well. So success of this particular project will, they are seeing around 50 or more trains, similar kind of applications in different parts of the world. It's called as an initiative of hydrogen for heritage. Initially we are thinking of the Jind one, and then later on maybe Darjeeling and maybe Shimla, areas where diesel trains run, and we are replacing those diesel trains with hydrogen train sets.
Okay, interesting, because CSTEP did look into one of these use of hydrogen for trains, especially in the hilly regions or where electrification is a challenge. I believe those are the areas the Indian Railways should be looking at. But I have a question to both Mr. Anil and Dr. Balaji, especially related to the safety of hydrogen. Safety in 2 aspects. One, with respect to handling those equipments itself, because hydrogen is a fuel that cannot be seen. Even if it burns, you can't see it. And given its propensity for the negative Joule-Thomson effect, and if it leaks out, it starts getting heated instead of cooling. So you have a fundamental issue. One is that aspect of safety. The second aspect of hydrogen leakage, because safety from a point of view, from a climate point of view in this case, that is, hydrogen leakage can result in offsetting the benefits of what hydrogen is being deployed for. How this has been addressed in the current technologies, I think both, if Dr. Balaji and Anil, if you can address it.
And also include the storage. Storage is also very vital area.
Yeah, it's a molecule which can pass through any grain structure. So how it is being addressed, and because if storage is solved, many problems are solved in a certain. So
coming to electrolysis part, we employ, we do a lot of hazard studies. We employ leak detectors wherever there is a chance of leakage. One thing good with hydrogen is the lightest molecule. As soon as it leaks, it simply dissipates to atmosphere. It goes straight. Because of wind, maybe it gets dissipated to some other part. But again, it depends upon the concentration of leakage. But we employ leak detectors and all in our electrolyzer technology to detect the leakage as well as safety measures. Like if I employ a containerized solution, if there is any leakage and system shutdowns, and immediately we start the evacuation fans and all, they evacuate the complete system to evacuate the hydrogen out of the system. That is one safety aspects we follow from the electrolysis point of view. But coming to storage, as Sir was saying, right now for this particular train project, we are employing 3000 kgs on ground high pressure storage, which is not done anywhere in India. Okay, there are 2 pressure levels. One is at 200 bar and another is at 500 bar. 200 bar I'm storing in type 1 cylinders, steel cylinders, and that is already approved by PESO. Type 4 I'm storing in, 500 bar I'm storing in type 4 cylinders, composite cylinders. Not yet approved. This is first time approved in India, and it's going to be employed for the first time. I am employing type 4, it is cyclable. I can use type 4 continuous recycling purpose and do filling daily, dispensing daily. So type 4 is a better technology in that particular part. So safety part, there are standards being framed. PESO has given a one-time approval to us. They are studying hydrogen as a molecule right now. We are developing the standards for safety. Electrolyzer, the OEMs are having their own standards. They are following some EN standards, which PESO is which India is trying to follow. But coming to storage, the safety standards are yet to be developed. We ourselves have taken a one-time approval, and we are sure of operating the plant successfully. But still, people are trying to employ 1000 bar storage as well in mobility, and that would be requiring a 700 bar dispensing into passenger vehicles. So that's again another challenge. Again, it is going to be one time. So we need to start first of all. PESO has not yet started. The whatever guidelines they are following right now, CNG guidelines,
Yes.
to keep safety distances of so much of distance for based upon CNG. But the guidelines are not made for hydrogen part. So still we are framing those guidelines with support of some ministries as far as European norms. We are following it at the moment.
Are there any permissible leakages allowed today, as of now? Because you're not even able to identify it, right?
No. From the electrolysis point of view,
Or
I mean,
observed based on your initial studies or any analysis. Because this should be tested before putting on ground. Hence.
Exactly. I mean, if you take the type 4 cylinders, the material itself will start leaking. It's a permeable structure. And there is a leakage. And how much it is allowed, they are not being framed right now. How much it is allowed and all. That is most important. So people are banking on steel cylinders.
Correct.
Again, steel cylinders, embrittlement is a problem. We cannot go for high pressures. In order to dispense, especially the mobility I'm talking about, you have to dispense a 350 bar or 700 bar. I need to have high pressure storages. 200 bar will not work out.
No, definitely. I mean, mobility, I think it's still far in my opinion, but believe more on the stationary applications or especially dispensing stations, like you talked about. Either it could be railways to begin with, or any other storage applications in any industry needs to know. I mean, your project can definitely, I believe, through a lot
Definitely,
of
that is what we're banking upon. Hopefully, this project, once we get commissioned and start working, first of all, the train has to run. That's most important. And then we will anyway fill the hydrogen inside the train. So,
from a materials point of view, Dr. Balaji.
Adding to his safety point of view, in the stationary applications, being R&D lab, we have dedicated PEM electrolyzer, which is imported from Proton. Actually, it's produced 5 kg per day. I mean, the safety aspect, as you said, it's much safer than LPG. It's a lighter gas, actually. So the sensor which are available, it's limited for low LE level, 2% actually. The flammable limit of hydrogen is 4 to 75 in the air. So the sensor which is being designed and which is available in the market is designed only 2% allowable. So once the even 2% leakage is there, then alarming the safety aspects is well proven, especially in the term of stationary application. And the material, as you asked the question, I mean the kind of membrane and the separator, which we need to concentrate more, and the precious metal usage, whether it is alkaline or PEM, though the nickel is being widely used for alkaline electrolyzer, but there are new concepts which is coming out from the chloralkali industries point of view. There are traces of platinum which is also being included in the alkaline electrolyzer, which will make alkaline water electrolyzer much life is being extended. So considering the usage of nickel and precious metal lightning, we need to think about the material research aspect. Apart from the electrolyzer development, there are other BOP components which is recovered for the electrolyzer, like IGBT based power supply system and the compressor, I mean hydrogen compressor maybe. So still we are depending on foreign countries to handle high pressure cylinders. So apart from the electrolyzer development, we need to consider other BOP components like power supply system and the compressor and all those things which also need of the other to realize the hydrogen economy here.
Okay.
Can I ask something?
Please, sir.
Address to both of you. Have you taken advantage of the PLI scheme? Are you part of the PLI scheme?
we wanted to take advantage, but there are no advantages to us. So
You
we.
will not shortlisted. Advantages are there, but
There are some advantages are there. We haven't bid for it, sir, first of all. So we thought like we can set up our own electrolyzer manufacturing capacity on our own, and we are banking upon executing real-time projects like the hydrogen refilling station for railways, which we are setting up on, and setting up on manufacturing plant for PLI for electrolyzer manufacturing will give you visibility first of all, but there is no demand for the electrolyzers at the moment. So demand is going to come slowly. We are banking upon some hydrogen purchase obligation similar to renewable energy purchase obligation. If that is there, again, then the demand for the electrolyzers would definitely increase. But at the moment of seeing around 1 or 2 years down the line, we haven't foreseen any demand for electrolyzers in the market. People are starting to set up to showcase that we have 1.5 gigawatt capacity, 2 gigawatt capacity and all. But on ground, there is nothing, no manufacturing plant being set up of that much capacity. They are slowly scaling up. We ourselves have started with 100 megawatt. We have our plans for going a gigafactory one and a half year ago. But right now, we are slowly scaling up. Goes baby steps.
But the steel company like JSW, which are going to a huge capacity, and as Naveen said, they are also going to set up a big electrolyzer capacity. So there is a demand, like Tatas also are contemplating. So I think there is enough interest in the steel industry for electrolyzer or to produce the RE.
Yeah, ultimately, sir, it has to boil down to the cost of hydrogen, which Mr. Naveen was saying. If those numbers are achieved, only scale will not work out here. I mean, we need to work on some R&D and policy interventions on the renewable energy supply. You know, what Mr. Naveen was saying, we achieved an RERTC of 4 rupees per kilowatt hour. But at what CEF? It is maybe at 40 or 60%, maybe 70%. We need to have a CEF of at least 80-90%. That will actually, reduce the cost of capex on the electrolyzer part. Instead of employing a 100 megawatt plant, I would be employing a 200 megawatt plant if the renewable energy capex is like, CEF is like 60%. So if I'm trying to reduce the cost of electrolyzers, at the same time, the cost of power also has to come down. So it has to be both. So what we feel as an hydrogen guy, we feel vertical integration means the generation of the power as well as the production of hydrogen. Both have to be at the same location. But what happens is the consumption point is somewhere away. Again, the transportation cost will be higher. So balance should be, we need to strike a proper balance between the energy, capex of electrolyzers as well as the production part.
And you will continue to focus on the alkaline process rather than going to the PEM because
no, we are doing right now.
OPEX is very high, perhaps.
No, I'll tell you one thing. We are doing right now PEM technology, proton exchange membrane. Its capex is double of alkaline, but the operational costs are quite less. PEM is a better technology with respect to its compatibility towards renewable energy. What you were saying, right? Because of its ramp rates and all those things. And since the OPEX costs are quite high, if you see the levelized cost of hydrogen, maybe alkaline and PEM, both would be the same because alkaline's O&M costs are quite high. Their OPEX costs are quite high. You need to replace electrolytes, you need to replace the stack refurbishment and all, lots of manpower would be employed. So ultimately, levelized cost of hydrogen is what matters to the steel companies, like cement companies who wants hydrogen at their battery limits. So they need to compare both the technologies, understand alkaline technology is a mature technology which people want to employ because its capex is quite less at the moment. But its compatibility towards RE is what the data points we require. And PEM, it is proven in the lab scale at least that it is very good to, it's a good technology to, integrate it with the renewable energy, especially with solar or wind.
And I'll maybe just to add what you are saying. See, I think alkaline is for alkaline the silver bullet is about the availability of the renewable energy round the clock. So alkaline compatibility with the round the clock electricity is absolutely paramount. If there is an intermittency in the renewable power, then of course PEM scores a higher points and compatibility than alkaline. But yes, alkaline, if you see the data points at this point of time, the capex is almost half as compared to PEM, and the two basically biggest orders that have actually got the final investment decision, that is Stegra formerly H2 Green Steel in Sweden. They have placed 800 megawatt of alkaline electrolyzer to ThyssenKrupp, and same as Neom, close to 800 megawatt of alkaline electrolyzer to again ThyssenKrupp. So I think starting point, alkaline is absolutely compatible, easy to deploy. And as we move forward, as Dr. Balaji rightly said, I think there's so much of work that has to be done on how we can increase the current density, how we can sort of increase, basically decrease the per kilowatt hour of energy that will go into the electrolyzer. One of you might have heard the company name, basically the company from Australia, HiSeta. They are, claiming 42, 43 units of electricity per kg of hydrogen, which is like close to 25-30% lower than what other manufacturers are claiming. So I think that is the area of basically the advancement or area of improvement that we have to do. Capex part, see, we have done this calculation day in and day out. Two most important things that really play around is, first is the per kilo, how many units of electricity per kilowatt per kg of hydrogen. The most important point. Second most important point is cost of capital. What kinds of cost of capital you are getting from the market. And third is probably the capex part of the electrolyzer.
Thanks, Mr. Naveen. But quick question to you, Mr. Naveen. Do you think RE is a bottleneck or a challenge? Because for hydrogen adoption, we want to see at least, if we want to look at even a million ton of hydrogen produced, you are looking at a 30 gigawatt of RE to be deployed. Do you think RE is a bottleneck or a challenge still going ahead?
No, I think RE is definitely not a bottleneck. See, it is not about RE alone. You see, the time lag that is happening now to get a grid connection or to get a STU connection. It is now, the time has gone up to 6 to 9 months. Right. So there is also the auxiliary infrastructure, the ecosystem that has to be developed. And to me, I think the grid that itself is a biggest bottleneck. So we have to augment our capacity. And I think the government of India, the Ministry of Power, they have already taken it. So from increasing the grid capacity from 135,000 circuit kilometer to 155,000 circuit kilometer. That is important, because the evacuation of power is super important. So I think that is going to be, what the biggest challenge will be, and how we can bring in, the micro smart grid, and with AI, I think we can also optimize the overall losses or the power synchronization. I think that is the second thing. And once we do this, I think the deployment of renewable power is super great. If you see the strike rate of renewable power, in last year, it is like happening close to 23 to 25 gigawatt per annum, which is actually number one in the world. So I think the deployment is absolutely great. It is about the synchronization via a power grid, and also the acceptance of the off-taker. That is super important. There is no business case to any of this technology if there are no off-takers. And that's why one of the, I think that a Ministry of Steel has also come, how to increase the penetration of renewable power in steel industry from presently 7% to 43%. That is also one of the main, precursors that they are going to sort of define, and that is where the end consumers have to be there. The off-takers have to come forward how they can improve, and the off-taker will come forward once the economics will start making sense, once there is a carbon price market, and also the willingness to pay by the end consumer. So all these things are interconnected, and all these things will be resolved one after another.
Okay, thank you. I don't have any further questions, but I think now we would like to open the floor for any questions.
Dr. Hazra is not there?
No, couldn't join.
Okay.
Thank you. Thank you for this insightful talk. My question is mostly to the steel industry panelists present here. So, Mr. Kashiva, you have written about the DRI dilemma, which is that DRI being a very carbon intensive process, and the scrap, which is the alternative, is extremely deficient in India. And with the talk around hydrogen-based, potential for hydrogen-based steelmaking in the DRI process, mostly in the natural gas-based DRI process, but India has most of the capacity in the coal-based DRI process. So in this regard, how do you envision the expansion or the of the DRI industry in India, given that most of the capacity is planned in the blast furnace route? And do you think that natural gas could be served as a bridge fuel until hydrogen becomes competent in the next 20 years or so?
Part of the questions I have replied. If we want to augment the steel production in the country, we have to live with the coal-based DRI. It is a fact. It is a practical proposition. That is why a lot of the capacity is still being set up in the country, all over the country, not in a particular cluster. Say, for example, Chhattisgarh or Odisha. It is developing very fast everywhere because these promoters are very much convinced that scrap is not available, will not be available from either internal sources or external sources. They are very sure. And setting up a BIBF route is a time taking. Perhaps in country no further greenfield BIBF plant will come. So that is why existing main producers are having a brownfield expansion. But there they will also have a limit. Yes, you are right. Transition should be take place from blue gas to the green hydrogen, blue hydrogen to the green. But again, there is a chain in natural gas. You will be surprised that last 32 years, not a gas-based DRI plant has been set up in the country. It is surprising, whereas as per their presentation, they have showed that green DRI base has got a 1.3 to 1.6 ton of CO2 per ton of the crude steel. It is the most eco-friendly route of making the steel. We have nothing to do anything to go for electrolyzer or for RE. Just set up the natural gas based plant, blue hydrogen based, and then transit subsequently when the technology matured, price are available at the rate of 2 kg dollar to 2 kg or 1.5 kg, then automatically transition will take place. But till now, I am actively associated with the GAIL, with the Ministry of Petroleum and all that. They are asking me why the plants are not coming forward. I've said your policies are not investor friendly. The prices keep on changing, fluctuating very fast, and then you are insisting for a last mile connectivity. That is a big problem. Why these fellows like Godavari or Tata Steel are not coming forward? Because the cost of last mile connectivity from their gas pipeline to my plant is a very costly proposal. Proposition. It takes 50 crore rupees per km kilometer to set up a pipeline. So I'm insisting you set up in the clusters. Then there will be a substantial increase in the use of, because people are very clear that there has to be a transition. There has to be a transition. But availability at the affordable price of natural gas is a big stumbling problem.
I think if I may just add one point here, see, I think it boils down to the economics. You see, today the only natural gas based DRI plant, it is in Hazira right now, and you know what is the landed price of natural gas they are getting? The landed price is close to $12 per MMBTU. Right now, if you compare that plant or that DRI versus the DRI plant there in Middle East, where the gas is hovering between $2.5 to $3.5 per MMBTU, the economics is not working out. Everything boils down to economics. So India, which is importing like close to 85% of the natural gas and oil, unless this $12 per MMBTU come down to $5.5 to $6.5 per MMBTU, the final mile collectivity and all this stuff. So I think they can definitely be a solvable thing. But economics is where I think the intervention has to be done. Once that is done, I think the rest of the things will fall in place.
I will supplement what Naveen said. Experts and economists are of the opinion that the price of natural gas in the future can come down to the level what he is asking, $5 to $6, Once the commercial availability of green hydrogen is established, people started switching over to the green hydrogen, then the demand of the natural gas will come down. It will definitely be available after say 10 years or 15 years at this rate what he is talking.
I think if the syngas is available and we have the CCUS technology, or you can say that the solutions, then that can be one of the option if you don't have the natural gas in that case. I think Naveen can throw a light on that.
No, no, absolutely, sir. See, right now we are operating world's only coal gasification-based DRI plant in Angul, and our cost is exactly coming to the range that I have said. Natural gas. So the only downside here is about the how we can patch in or hook in the carbon capture utilization, because that is the only thing. And I think in next 1 year we are going to also establish this as well. Then I think. Coal gasification with CCUS, I think nothing can beat the economics of this combination in even in next I think 7 to 8 years. So I think as a good transitionary or a transition phase, I think for India, again, I'm very specific for our country, this can be one of the best way forward where we are also, and why not only syngas based DRI plant, even for hydrogen as well. If coal gasification can be coupled with CCUS, the hydrogen, the levelized cost of hydrogen, Mr. Anil, that we can get from this combination, it is 1.5 to $1.6 per kg, and which is exactly the sweet spot. If this price can be managed or maintained, or delivered price can be maintained, then all the steel maker will join the bandwagon.
Well, hi, my name is Sharat. I'm with Center for Social and Economic Progress. I have two questions. One question, sir, because there was briefly alluded towards carbon credit trading scheme. I mean, it's still some time away, when that scheme is going to be established. But I think the whole process is going to start. I think the benchmarking and the guidelines, everything will start flowing through. And the sense is like hopefully by next, maybe in early 2026, some things will start flowing. But my question is over there, sir, how prepared is the steel sector towards the carbon credit trading scheme, given that if the scheme starts right now, and if you have a benchmark set? Like my question is like, what percentage of the plants, I mean, considering that, it's exactly the PAT mechanism that's going to be followed. And you will have that, these set of steel guys are going to, they have to meet the targets. So what percentage of steel sector is kind of prepared for that? The second question is got to do with, again, the conversation also alluded towards CBAM. Now the question is, I think there's a big debate over there, considering the carbon price in India versus the carbon price in EU. And there's a significant difference in the prices. How do you see that, how can that be bridged? Or do you see any other thoughts, like whether we can think about in a different way, we can start talking with you, hey, you know what? Let's not talk about the differential. Let's start talking in this direction. Leaving aside the topic of, hey, we are in developed nation and all that. Yeah, those are the two questions. Thank you.
Naviji, would you like to react, or I should react first?
Yeah, maybe I can just briefly, answer that question. So, see, I think the steel industry is definitely prepared. I think it is about right now. You might have seen the carbon prices market as well. Last 1 year has seen the biggest downfall of the carbon credit market, where the prices have almost crashed from $25-30 per ton to almost $4 to $5 per ton. Right, and the basic reason and the main reason for this is about the greenwashing. So many frauds have come in the market due to this greenwashing, and that was the biggest fault. So I think the carbon market is now, I think, getting stabilized the way the way the hydrogen market is also getting stabilized. Only the serious players, only the serious avoidance practices that really reduce the carbon intensity going into the atmosphere, those are getting the real benefit. And I think it is going to go more and more mature. Steel plants, I think there are so many practices that we are, I think, adopting, and which we are going to adopt. And there are so many. So I always, tell my department that how we can convert it from a cost center to revenue center. And one of the revenue stream that we can create is the carbon credit market. So I think the avoidance or valorization of off gases, the coke oven gases, and the carbon capture utilization is, I think, the quick wins that are available for the carbon credits. So I think as more and more technology will become more scalable, it is mature right now. It is about scalability of the technology, and also the premium. As I said, the willingness to pay will dictate all these things. Once the willingness to pay is there by the customer, and I am now very specific to India. There is definitely a willingness to pay in Europe. There is definitely a carbon market that has already matured in Europe. I think we have to also follow in the same line. Why in Europe it has, the transition is easier because they already have the emission trading scheme, ETS, that is already ongoing there. So it is mature, especially for the hard to abate sector, there is a quota that has been given to these guys, and they are trading those, balancing, offsetting their carbon intensity with this quota. But I think coming CBAM, where they are going to bring the parity among all the steel makers, that is where I think they will also align with the overall global practices, and we as well. I think once there is a parity, then definitely all these things will start falling in place. So that's about carbon credit market. So I think the policies, the willingness to pay, all these things have to fall in place. Once that is there, I think it will more or less streamline. That's my view.
Let me try to respond to your specific questions. The preparedness of the industry. As you said, industry is prepared, but since you have brought the PAT scheme into the discussion, BE is already engaged for the measurement of the baseline. They have covered lot of the industry. They have got a data. Then the second things will come MRV. Then what they have measured, what their certified energy auditors have given to them will be verified. So that things is already progressing very fast. Now about the carbon credit price and all that. Presently, there is no market. Many of my members have crossed the limit which has been the target which has been specified by the PET. Under the PET, I am a member of that committee. But when they go to the market, they pin me down कि you're forcing us कि ये करो वो करो ये करना है वो करना है. But when I've done all these things, when I've reduced my CO2 emission, and when I go to the PET committee or the carbon credit this thing market, there is no buyer. So we have to, and the price, the CBAM price or under this thing, the incentives will really come because of the two factors. One, what is the credit I am going to earn before putting the capex? Second is that what incentives, financial incentives are being given. That Ministry of Steel, which they have released the taxonomy, they have talked about the interest subversion of 3% to the SSI units. Like these incentives or purchasing of a green steel, if some incentives are there, then these will be the great motivators. Thank you. I think I have replied to your question to yourself.
Sir, I mean, just one ad. Just correct me if I'm wrong, or sir, because this is Naveen sir brought this up. But I did look at the price in EU market, sir. I mean, this is a little this thing. I think it peaked at 120 euros, and now it's at almost 80 or 78 euros right now. But I might, but that's why I was a little confused when you said $20 and then you said $5.
No.
I was a little confused.
I'm talking about, my answer was very specific to Indian market. So
Got it.
last year, if you talk about ETS, it went up to $110 to $120. Right now, it is hovering around $65 to $70
Correct.
or euros per ton.
Correct.
So my question was very specific to the Indian market. If you see the carbon credit market at this point of time, it is around $3 to $4 per ton. And the major reason of the downfall is about the greenlands, because all those avoidance and solar and so many plants, they were taking the credit, and because of the greenwashing, the market has almost crashed. So the focus area right now is avoidance. How we can avoid? So direct air capture is one of them. Second is carbon capture utilization, basically storage. So permanent sink is where it is really getting the traction.
Thank you all for your very engaging participation in the panel discussion. I would now like to invite Jay to please hand over mementos as a token of our appreciation to the panelists. Mr. Paranjeet Singh.
Thank you, sir.
Mr. Deependra Kashiva. Dr. R. Balaji. Mr. Anil Srikar Puvluri. Mr. Naveen, our token of appreciation will reach your office. Thank you so much for joining us today.
Thank you so
I
much.
now invite Mr. Thiru and Murli to give the vote of thanks.
Again, thanks a lot for all of us who have had an engaging discussions. So what started as, I'm reminded of the Eden Garden test match here. The first innings was a clear follow on, the first half of this event. But the second half, I really liked the way the conversation progressed and was quite engaging. Thanks a lot to all the experts and my team, especially for putting this event together. And again, it's one step in the right direction. And I've spoken to people individually and collectively. I'm saying hydrogen. In a very tongue-over-cheek way, let me conclude it this way. Hydrogen is like Starbucks coffee. So while filter coffee has its place, those who can afford Starbucks coffee will have to go there, should CO2 is of interest to them. With that, I think I'll conclude this session and lunch is there served. Please. Thank you.